Welcome. In this video, we are going to talk about intermolecular forces and what these intermolecular forces are and how they determine the properties of molecular covalent substances. And this can go along with a note sheet. So you should be following along, taking some notes on this if you missed that in class or just want to review it to catch up on things. Okay, so we're looking at what holds stuff together. So like if you have a glass of water, what forces are holding everything together in that water? Well, it turns out there's two different types of forces. There are bonds between the atoms. We call those intramolecular forces, although often we just use the word bonds. Okay, and that's what holds the atoms together within a molecule. And then when you have more than one molecule together, there's a different type of force that's holding the molecules together. Those forces are called intermolecular forces. And here's a visual for you so you can see the difference here. So if you have a glass of water, then there's two different types of forces within that glass of water. So you've got the bonds holding the hydrogen and oxygen atoms together. That's, within a single molecule, right? So this is a molecule. These would be the individual atoms. So the bonds hold the atoms together within a molecule. And then there's a different type of force that holds individual molecules together. And we know atoms and molecules are really small. If you were to have, it turns out if you were to have 18 grams of water, that's about a mole of water. And remember, a mole means you have 6 times 10 to the 23rd molecules of something. So you have an awful lot of water molecules bumping around in a glass of water. So what's holding those water molecules together are these intermolecular forces. And it turns out these things have a really big impact on the properties we observe. So these intermolecular forces affect the properties like melting point, boiling point, evaporation rate. These are all things that we can observe that are determined by the intermolecular forces that are found within a sample. Surface tension of water, that's another property we can observe. So intermolecular forces explain why water boils at 100 degrees and why oxygen is a gas at room temperature. These properties of water and oxygen are related to the forces holding the molecules together. And so we're going to talk about what those forces are. So again, properties, re-emphasizing the point, properties are determined by the intermolecular forces. It's the forces between individual molecules. So here's another visual. This is showing the HCl molecule. This right here with the solid line, that is the covalent bond between the hydrogen and chlorine atom. And then the dotted line we're using to represent the intermolecular force between these individual HCl molecules. Intermolecular forces are much weaker than actual bonds, and it's the intermolecular force that tends to impact the properties. And the reason why is because most things that happen, like evaporating or melting or turning into a gas or dissolving, like when you dissolve salt in water, for example, all of those processes involve the breaking the intermolecular attractions, not the bonds. So when we melt something, no bonds are broken. We're just overcoming these weak intermolecular attractions. And so the type and the strength of these attractions will determine properties such as boiling point, melting point, evaporation rate, solubility in various substances. So there are three types of intermolecular forces that you want to know. There are dispersion, and dispersion forces are found in all molecules, no matter whether you're polar or nonpolar. Dipole forces, these are a special kind of force that's only found in polar molecules. They're a little bit stronger than dispersion forces. And then the strongest of all is hydrogen bonding. And this will happen with polar molecules that have a certain bond in there. So if you have a molecule that contains an OH, NH, or FH bond within the molecule, then that molecule will be able to hydrogen bond. And so we'll look at some examples of these three. All right, so the first intermolecular force we're going to look at is dispersion forces. And remember, dispersion forces exist in all molecules, polar or nonpolar. It's caused by the random motion of electrons. So the electrons within the molecule, within the individual atoms, are moving around. As they move around, they create these moments of partial positive and negative charge. And that is what causes the dispersion forces, is that movement of electrons cause, we call this momentary dipole. We're going to have this slight positive or negative charge. That's what results in that attraction. But the main thing you need to worry about is that since they're caused by the motion of electrons, it turns out the more electrons there are, the stronger the dispersion attraction. So as a result, larger molecules, meaning like molecules with larger electron clouds, with like more shells of electrons, are going to have stronger interactions than smaller molecules. And here's some examples. Propane has a boiling point of -42. It's a gas at room temperature. Octane has a boiling point of 125. It's a liquid at room temperature. And if we look at the structures of propane and octane, they both contain all carbons and hydrogens. Turns out these molecules are both non-polar. We can say it looks really the same all the way around. They're very symmetric. So these are both non-polar. But octane has a much higher, what do we say here? If we looked at its boiling point, it has a much higher boiling point than propane does. And that is because it has it's a larger molecule. So it's got a, larger electron cloud. You would say, you can think of it as there's more kind of electron shells here. There's more electrons that can interact. And so the more electrons you have within a molecule, the stronger those dispersion forces will be. So it's going to be, these molecules will be held together more strongly than propane molecules. So that was dispersion forces. Dipole forces, these only exist within polar molecules. And we call it a dipole interaction. We think di means two, so it's like two poles, right? So these are with molecules where they have two poles. Those two poles are positive and negative. So if a molecule is polar, that means it's got a positive side and a negative side. And when you line up two of these polar molecules, the negative side of one molecule is going to attract the positive side of another molecule. They're going to be like magnets, right? So they're going to attract each other. And that is a dipole interaction, negative to positive attraction. It only occurs within polar molecules. And this is going to be a stronger interaction than the dispersion forces. Okay. Dispersion forces are in all molecules. They tend to be a little bit weaker. Dipole interactions are only in polar molecules. They're a little bit stronger. But the strongest of all the forces is hydrogen bonds. Let's go look at that one next. So hydrogen bonds, this will only occur in molecules that have an H bonded to an N, O, or F. These molecules will also always end up being polar as well. So the molecule will be polar and it will have an H bonded to an N or F. And here's an example, like water. In a water molecule contains an H that's covalently bonded to an O. So that means this water molecule is capable of hydrogen bonding, which means what hydrogen bonding looks like is if you have two water molecules near each other, it's the attraction between this hydrogen and this oxygen. This is what we call the hydrogen bond. And the reason why this hydrogen bond is so strong is because this HO bond and the HF and HN, these bonds are very polar. So it's a very polar bond. So you end up with strong, positive, negative charges within that molecule. So you end up with a strong attraction between those molecules. So that's what a hydrogen bond looks like. So again, it's pretty similar to just a dipole attraction, and that the positive side of one molecule attracts the negative side of another molecule. It's just the difference here is when there's an H bonded to an O, N, or F, that bond is superpolar, and that just makes this attraction much stronger, that we just give it its own special name. We call it a hydrogen bond. All right. And hydrogen bonding is something that is important to you. You might not realize it, but hydrogen bonding is what holds together DNA. So we talk about the two strands in DNA. You might remember talking about DNA replication and how the two sides kind of unzip to kind of form new DNA. And we talk about kind of, unzipping the DNA. It's hydrogen bonds that are holding those strands of DNA together right down the middle. So these right here are all hydrogen bonds. So you've lots of hydrogen bonding happening in your body right now. And your body is also made of mostly water, and we know water molecules are attracted to each other by hydrogen bonding. So again, lots of hydrogen bonding happening. So if you think about the impacts of these various intermolecular forces, let's compare boiling points. We look at hydrogen gas, hydrogen bromide, and hydrogen fluoride. So hydrogen, H2, it's nonpolar, so it only experiences dispersion forces. HBr is polar, it has dipole-dipole forces. HF molecules can hydrogen bond. And if you look at their boiling points, notice that HF has the highest boiling point. That's because hydrogen bonding is the strongest attraction. So when you have a stronger attraction between molecules, you'll see a higher boiling point. You also will see a slow evaporation rate. Okay, so what we're noticing here is the stronger the IMF. So when you have a stronger IMF, it just means the molecules are going to stick together better. So those HF molecules are more attracted to each other than those H2 molecules are. So HF has a much higher boiling point, H2 has the lowest boiling point. So that's one example. Here's another example, propane versus acetone versus ethanol. Again, we can see the one with the hydrogen bonding has a higher boiling point of them all. Propane, which is nonpolar, notice how it's the same all the way around, it's totally symmetric. It only experiences dispersion forces, which are relatively weak. So it's got a lower boiling point. It is a gas at room temperature. Acetone is polar. It is a liquid at room temperature, but it evaporates really quickly. So it evaporates fairly quickly, even though it is a liquid at room temperature. And then ethanol is polar and it contains an O bonded to an H. That means that ethanol molecules can hydrogen bond to each other. And that's going to be the strongest attraction. So it's going to have the highest boiling point. It's going to evaporate the slowest of these all. And this slide is a comparison between intermolecular forces and bonds, just to let you know that intermolecular forces are much weaker than actual bonds. And if you think about it in terms of energy, intermolecular forces would take between 2 and 20 kilojoules of energy to break a mole of those bonds. We haven't talked much about what kilojoules mean, but just know that that is a measurement of energy. Whereas covalent bonds, it looks like these take at least 10 times as much energy to break those bonds, and ionic bonds can take even more energy. So that is why network covalent substances and ionic substances have such high melting points, is because when you have network covalent or ionic substances, in order to melt those substances, you're actually having to break actual bonds. And bonds are much stronger than intermolecular forces. So the only type of substance that actually experiences intermolecular forces is, well, look here in the name, molecular. The only type of substances that experience this are molecular covalent. And you might remember from doing a lab earlier that molecular covalent substances have relatively low melting points compared to ionic substances or network covalent. This would be an example of a network covalent. This would be an example of an ionic. So the reason why molecular covalent have such lower melting points is because they're held together by intermolecular forces, which are much weaker than actual bonds. If you want to actually break a bond, it's going to take a lot more energy. So these ones are going to have much higher melting points than your molecular covalent substances. All right. So looking at a practice problem, why is water a liquid and oxygen a gas? Well, first we have to consider what's the structure of these molecules. So water, and then determine if they're polar or nonpolar, then figure out what IMFs are present. So if you take a look at water, here is water. It's got my oxygen has 6 electrons around it. Then I'm adding a hydrogen here and a hydrogen here. And this shape is bent, and it is going to be polar because it looks asymmetric. So if it is polar, we know it can have dipole forces, but we also want to look out for, can it hydrogen bond? So if it's got an H bonded to an O, an N, or an F, it's capable of hydrogen bonding. Well, if I look at this molecule, it looks like it's got an H bonded to an O. So this molecule can hydrogen bond. So let's draw this out of what this looks like. So when you say water can hydrogen bond, what that means is when you have several water molecules together, the hydrogen from one molecule is going to attract over here to the electrons on this oxygen right here. And this right here, often we use a dotted line to represent it. This is what we call a hydrogen bond. Here's another example over here. This would be a hydrogen bond. It would be the attraction between this hydrogen and these oxygens. I'm going to erase my electrons because I feel like that's getting confused with the dot picture. Okay, so it's the attraction between the hydrogen on one molecule and the oxygen on a nearby molecule. That is what a hydrogen bond is. Remember, it is intermolecular, which means it is between two or more molecules. Okay, so those are the hydrogen bonds here. And hydrogen bonds are relatively strong. All right, now let's look at oxygen. I know I'm kind of running out of space, but oxygen looks like this. Here's the Lewis dot structure for oxygen. Notice how this molecule is totally symmetric. It is nonpolar. And if you look at a molecule that is nonpolar, so it can't hydrogen bond, it can't do dipole forces because it's not polar. So the only force it's going to have is dispersion forces. Remember, dispersion forces are present in all molecules. And dispersion forces are relatively weak. So if I were to draw that out, what it would look like is just, when you have these oxygen molecules nearby each other, the attraction between them is what we call a dispersion force. And it doesn't really matter how we orient these oxygens relative to each other because they're the same all the way around. They're nonpolar. So this is a dispersion attraction. It is relatively weak. The hydrogen bonding over here is relatively strong. So that is why water molecules stick together in a liquid form at room temperature, whereas your oxygen spreads apart to make a gas. So remember, when you're a gas, your molecules are really spread out. And they're going to spread out because they're not very attracted to each other. Whereas in the water molecules are pretty strongly attracted to each other, so they're going to stick close together and stay as a liquid. All right, so that's a little summary of intermolecular forces. Please follow up with any questions you may have.